or a beam. And this one was down at, this problem was solved at University, not at Virginia Tech. It's published, it's in the literature. So, and it's something like 20, 25 years ago. It's not anything recent. So, if you take an elastic plastic plate, the stress strain law is shown here. Like it's elastic, perfectly plastic material. And you apply a pulse, pressure pulse, it's uniformly distributed. In this case, the load is going up, but doesn't matter though, right? Whether it's coming down or going up. And you apply pressure for T0. So the critical things are the magnitude of the pressure P0, the height, and the duration. Depending upon the yield stress of the material, thickness of the plate, the length A or L, we can find P0 and T0 so that the response looks something like this. Now if you see, the load is acting up, right? The plate is bending down. Number one. Number two, I think many of you asked me when I was doing the beam problem why the load is acting up, but we were doing a linear elastic problem, so it was deflecting up. But this one is a elastic plastic problem. The normal expectation will be that the center of the plate will move up. But as you can see, it moves up. And then it stays below the undeformed state. So it's negative. It's reciprocal or inverse of what we intuitively expect. Number two, these are the solutions of the same problem with 8 different codes. And you choose which one you like. Some of them do give you deflection up. Others give you deflection below the undeformed state. I think the point is the solutions are different. So I don't know which one to accept. All of them are based on the same equations. So basically the coding issue is a problem, is causing these things, yes? Oh. Oh, it was not. Okay. Now the ornament is fine. So you can see that whether you can trust the solutions or not from a code. I cannot tell you what you should do. Also, if let me see if I can. Yeah, the picture may or may not be very clear, but as I said earlier, that I generally assign a problem that you choose your own, and so this student is a different class. It's the same course, but it's a different class, like it's a different year. So he designed a stiffness matrix, and if you see the entry KE13 is -7/3, on that side is +7/3. On this side is 8/3, on that side is -8/3. So he purposely did that. But the solution of the problem made no difference whether there was a minus sign or a plus sign. Pardon me? I'm not sure if diagonal terms were negative. But whether they are negative or not, the problem is there's a mistake in the stiffness matrix. The solution does not show you that. When he refined the mesh, both solutions with the correct and the incorrect stiffness matrix were basically giving you the same convergence rate. So how do we find error in the code? So in this case, what happens is the rate of convergence is not correct. But this is a linear elastic problem. So you can estimate or you can find the rate of convergence when you refine the mesh. For a nonlinear problem, the one I showed you before, we cannot estimate the rate of convergence. So there can be bugs in the code, and you may still be getting quote unquote very good solution. It's possible that for a different loading situation, this stiffness matrix would have given us a wrong answer, a wrong solution. So it just so happens that for the problem he studied, when he purposely introduced the error, changed the sign, it did not make any difference. So the caution is that you have to check your code again and again and again before you say, yes, it's fine. Yes. Oh, any question or comments on this? No. You are getting the no. Oh, previous one. Yes. I don't know. It's whether. So that's what you expect for the membrane, that it will stabilize down? I mean, that's what you expect if I had not shown you? I don't know. If I would have thought if you are applying the load up, it should go up. But it doesn't, it goes down. Yeah, so it's not what you expect. I mean, some codes gave you plate deformed up or the membrane deformed up, but other codes gave you the opposite shape. He knows. I don't know which code is correct, because we are solving the same equations. That's a good experimental. No, but there is no experimental data shown on that one. I think the exercise, the purpose of that exercise was whether you should trust commercial codes or not, even though that was not the title. Recently, Professor Bazant from Northwestern, he published a paper in, I think, Journal of Applied Mechanics or Applied Mechanics Review. The title of the paper is Error in Abacus. I'm not brave enough to publish something like that error in abacus. Like there was an error in post-processor of LS Dyna. The sign of the shear strain terms were reversed. So it's our fault. We did not catch it first. But after 2-3 years, we realized that it's a post-processor that is causing the problem. So we published, but we did not say that error in post-processor of LS Dyna. Actually, we said we were modest. We said we could not catch that error in time. For when we initially published the paper, that this sign in the post-processor was incorrect, but we did not blame the developers of LS Dyna. We blamed ourselves that we did not catch it. So I was not as brave as Bazant. Hey, error in post-processor of LS Dyna, or error in LS Dyna, error in abacus, error in labs. I mean, so far we have found errors in all of these codes. Whether they are significant, in some cases they are significant, in other cases, well, I don't know. Error is an error, right? Whether it is significant or not. If you get temperature rise, which is 1/8 of the actual value, or close 1/8 of the real value, then it's a big error. Because your material is softening, so it won't be softening at the right rate. Okay, so I think that's basically, I mean, I have so many plots, but I don't think I'm going to go through all of them. So any questions you have that you want to discuss before I use the chalkboard? Anything on your mind that you want to ask? Yes?
It is slightly off the track.
Well, if it is off the track and I don't know the answer, I will tell you I don't know the answer.
Suppose we have taken a plate system, 400 plate.
Oh, wait. You said 400 plate?
Planar.
Okay, 2D plane strain or plane stress problem, right?
Plane alignment. So this section. Now, I mark that critical section because I consider it as a rectangle. I define the mesh furthermore. Let us take a rectangle element, rectangle. If I'm able, this is at 4 points, the critical section, triangle critical. Is that technique? Find stresses at 4 nodes and then find a stresses at each critical section.
I think maybe somebody in the audience will answer it because we talked about it. So, yeah, I know you were sick, but anybody will help him up? So basically he's asking, can we trust stresses at the nodes?
And if we have found the stresses at the section edges.
You don't find stresses at the edges. You do not, when an element work, you do not find stresses at the boundaries of the structure.
The critical edge.
Well, I don't know what is critical, but whether it's critical or non-critical, stresses at the edges are not correct. You should find stresses at the interior and then extrapolate to the boundaries. You cannot find, I mean, you can, but they are not good values. You should not find stresses at the boundaries of an element, period. Okay. Pardon? They are most accurate at Barlow points, B-A-R-L-O-W. Or you can, his question was where they are most accurate, not where you should find them. So if you want to find, if you want to say where they are most, again we are talking about linear elastic problems. So they are most accurate at Barlow points. And where are Barlow points? That depends upon which element you are talking about, whether it's 8-noded element or 4-noded element. Again, these are two-dimensional problems. No. So nonlinear problems, you always keep on praying. Pray. Sorry, I mean, that's the way life is. What can we do? I showed you, right? There were 8 codes. So if one does not think carefully, then we may be designing something totally wrong. When I say pray, you do iterations, you do small variation of parameters to see if by changing small, that's an interesting point. I don't think any one of you is going to believe that. Let me see if I can show you right now. I have it, I think. Okay, first the problem is that we are shooting a bullet into this block of gelatin. Gelatin is a simulant for soft tissue. Like if you want to simulate what is happening to our body if we get hit by a bullet, we usually use gelatin. It's a kind of jello. You make it out of bone powder. So you take bones of animals or cadavers, and then you need to grind them into powder, mix it with the right amount of water at the right temperature, and make this test specimen. So this test specimen was hit by a bullet, and what I want to show you is, well, the code, which is LS-DYNA, it predicts qualitative feature reasonably well. By that I mean results agree with, qualitatively they agree with experimental observations. And since we talked about very small thing and my statement about praying, so that's what I want to illustrate. So this is how the bullet travels through the gelatin, and things look okay, but they don't look terribly bad. Pardon me? Well, it goes out of the gelatin block depending upon the speed. Now I need to find where we change the speed by very small amount. Okay. Let me see if I can blow it even further. Okay, see, for impact speed of 6 to 124.9997 and 6 to 124.7 meters per second, the difference is 0.12345%. But the residual speed changes a lot. So the residual bullet speed changed by 2%. When you change the input by 405.405%, you just change tiny bit, and the residual speed changed by 2%. So that really means the results are highly sensitive to the impact speed. So what do we do now? Pardon me? Yeah, but I cannot do experiments. See, problem is, purpose of the codes or mathematical models is that once you have validated it, then you should be designing components based on the numerical work, not based on the experiments. I mean, if we had to design everything based on experiments, I would have been out of job 20 years ago, 30 years ago. Nobody will take my class. And if nobody takes my class, I mean, why should the university hire me, keep me? I mean, they can hire instructors to teach statics, dynamics. They don't need me or a person of my background. So that's the problem. So I don't know how to fix, how to overcome these issues. I think that's what you asked me. For nonlinear problems, what should we do? And my prayer is meant to overcome things like this when I'm changing input parameter by such a small amount and my output changes by a large amount. Everything plays a big role. I don't know if the material model of the gelatin really plays, because we use these material. I think it's elastic plastic, elastic plastic. So it's nothing fancy. Hyperelastic will be purely elastic. And then you should not be expecting a lot of deformations. As I said, qualitative features are fine. The code predicts results qualitatively, which you see in experiments. But it's highly sensitive to the impact speed. This was not our idea. We did another problem, different one. And that was the impact of a solar panel, like glass, at 3 kilometers per second by a steel particle or aluminum particle of, say, 2 or 3 micrometer in diameter. That's to simulate space dust. And space dust is hitting a satellite, say. So the reviewers came back. There were 3 reviewers. One of them said, why don't you change your impact speed from 2 kilometers per second, which is 2,000 meters per second, to 2,000.001 meters per second, and show us that the results don't change much. So we started wondering, how come this guy, this person thought of this change small? We Googled it. We know who had done it first. There was only one other paper that had done something similar. So we knew who the reviewer was. But that doesn't matter much, though. But somehow, when this reviewer studied the problem, not exactly glass impact, or impact on glass, they saw significant difference. When I say significant, because when you are changing input by 0.305% and you get the output by 2%, it's a significant difference. So they saw the same thing, similar. For impact problem, there also they had impact speed of like 2 kilometers per second, and they changed by a minute amount. With our code, with Abacus, we did not see that. Okay. Now, whether it's because the student who saw it, his mesh was not very fine, I don't know, I cannot answer that question. Or the crack length we were measuring, we were not measuring correctly because we were deleting elements. I have not talked about that, but I will say. So we were deleting elements, failed elements were deleted. So basically the minimum crack width was the width of an element, minimum crack length, extension in one was the element length. So whether we missed there, but we did not see that much effect. So when this student or this colleague, he submitted the manuscript, before submitting the manuscript, I said, you must do this. So the reviewer says, why are you guys mad? Why are you doing it? You are changing the impact speed from 624 to 624.301. Take out this part. It's nonsense. Seriously, that's what he wrote. We don't know whether it's he or she, but that's what the reviewer said. This is waste of time. Everybody's waste of time. So we said, no, we don't want to take it out, because we want to let the people know that the results are highly sensitive to the impact speed. And this is another reference that we had already quoted, but we had to remind the reviewer that, see, we are not the only one crazy people in the world. There is at least one more crazy person. That paper was also co-authored by 2 persons. I think at least there are 2 more crazy persons. But finally, now you saw the final version, so it was accepted and it's print. So I think the answer to your question, because you said nonlinear stuff, I cannot guarantee it. So you really have to do sensitivity studies, and even if you do sensitivity studies here, you are basically saying my results are, I cannot tell you what is the error in my results. If you change the angle of attack a little bit, things change a little bit. But if you change the impact speed a little bit, my best guess is, no, this is only a guess, because our codes have if statements. We say if the effective stress is greater than the yield stress, or if the effective strain is greater than 0.2, the delete this element. So that is where the problems come up, because if the effective strain is, instead of saying, when I say 0.2, it is 0.199999, it won't delete it. And if it is 0.2 and it is in the 10th decimal place or 20th decimal place, there is 1, it will delete it. So I recently had a student who graduated. So he was using damage. I think some of you have been asking me damage. So he was using abacus. So he gives me plots. He says damage is 0.59. Of course, the element is not deleted because it has to be 1 for it to fail. I said, come on, this is garbage. I mean, how can we trust, how can we tell anybody this is 0.99999, 5 times 9, and we are not deleting it? And I'm not going to sign on it. So he kept on pleading. Every time he will come and make an excuse. When the reviewer said no, then he did it. He revised it. Basically, he had to replot every data, because the if statement in abacus, when it says 0.59 and it has not failed, basically the problem is that if statement is not, it's instead of saying no matter what we say in the if statement, that question does not go away. Whether you say 0.95, then why not 0.949999? I don't know the answer. I mean, I do not know what should I tell you, because that if statement is an if statement, and it's not, there is no human person, artificial intelligence will help. Once it has matured, then artificial intelligence will pick it out that, oh, okay, even though this element has 0.59s and I'm not failing it, but the surrounding elements have failed, so this is a goof up, it should have also have failed. But our codes are not, at this time, they are not sophisticated enough to figure that thing out. Because it takes computing power again, and also somebody has to code it. Okay, so now let me talk about the zero energy deformations, like hourglass control stuff that I just mentioned in the beginning. So now I'm going to use the chalkboard, so I don't need my, so please, we can turn off the projector, so I can draw this sketch. Okay, so I think I don't need, well, okay, thank you. So is this chalkboard okay? So let's take this element. This is a 4-noded, the way I've drawn it is a square, but it's a 4-noded rectangular element. So if it deforms like this, so in the dark color is the deformed state, in the blue color is the undeformed state. So what is the strain here at the centroid? 0, very good. So if I am using one-point integration rule, that one-point integration rule says that you use your integration point at the centroid. So there is no energy used, even though the element has deformed. So these are called zero energy modes or spurious modes, and they create problems. It is very common to use one-point integration rule in large deformation problems or even in not large deformation problems. It's very common because you have, say, million elements. So it's very common to use one-point integration rule. So to be careful to avoid these situations. So to check, you should print out energy of zero deformation modes. And if that energy is, in your opinion, a significant part of the work done on the system, then don't do it. Or use 4 points. Okay, that's expensive. There are spurious control algorithms implemented in different softwares. So they have, like in LS-DYNA, there is more than one spurious control algorithm. So try a different one. Don't accept the default one. So if you try a different one, then you will see that your answer will change. I turned on my computer, but now I realize I could have shown you an example. So typical case is that you take this element, you divide this into 7 elements. So it's 3-dimensional. So you take a cube, you divide this into 7 elements, and if you do either say tension or compression, I did not divide this into 7 elements because they give you how to divide this into 7 elements. Okay. It's homogeneous deformation. So if you plot the stress strain curve, effective stress versus effective strain, for each one of those elements, you should get the same curve. If you use default spurious control algorithm in LS-DYNA, you will get 7 different curves, one for each element, which is not right. If you change these spurious control algorithm to something else, another one, then all those 7 curves become basically collapse. You are still using one-point integration rule, but you are using a different control algorithm, different algorithm to control these kind of modes. And maybe when I know where I have on my computer, whether I have downloaded the paper or not, but it's in one of the papers with Guy Manton. So he checked the code. He did that test. With default algorithm, you get 7 different curves. With Velichko-Bindeman algorithm control, you get the same curve for all those 7 elements. So that tells you which control algorithm you should use in LS-DYNA. I mean, if you are using Abacus, that is a different story. You have to use a possibly different algorithm. Pardon me? You write your own code, you have to be, so either you avoid using one-point integration rule. Of course you will get, it's a mathematics, if you don't use any control algorithm, then you will get spurious modes with one-point integration rule. Doesn't matter. Doesn't matter whether it's linear or non-linear. We did not say anything about linear or non-linear, right? Doesn't matter. I do not know the details. I have not studied the details of that control algorithm, so I cannot answer because I don't know it. Okay, now I think I said also constraint problems. Oh, he left. Somebody defined incompressible materials and that person took a break. So let's say I have an incompressible material and my mesh is like this. I'm going to draw now. So these two edges are fixed. I'm just cooking up examples. This is in Hugh's book, it's not my own invention. So, but I have to show you that mesh can lock. Lock means all nodes have zero displacement. That's what we mean by locking. Like you lock the door, so the thief cannot open it. So that's what will happen here. Nodes will not move. It's an incompressible material. That means for the two-dimensional problem, area cannot change. Third dimension, nothing is happening. So there's no movement in the third direction. Okay, so if you buy that, area of this element cannot change. By assumption, right? So how can this point be, in which direction can this point be moved if this is a node to this element, this element? What is area? Height times base. Base is fixed. So height cannot change. So that means P must move horizontally. Right? Now look at this, it also belongs to this element. This height, this dimension does not change. So P must move vertically. So one element says, hey, move only horizontally, the other element says move only vertically. Can it decide which way it should go? But to satisfy both constraints, it cannot move anywhere. Right? So if this doesn't move anywhere, then you can go to this one, same argument. You can go to this one, same argument. But same reasoning, right? So that means none of the nodes can move. Doesn't matter. Because this is independent of the loading, right? Oh, you came at the right time, sir. We were discussing the problem you answered correctly. Incompressible materials. So so we are doing two-dimensional problem. That means area cannot change. And now, if you have a mesh like this, one solution to this is don't use a mesh like that. That way, that constraint won't show up. Like if I change my mesh so that I don't have some like well-structured mesh. This is again, these are cooked up examples. So I'm not saying that you guys are going to use a mesh like this. But if you did, the point is, for an incompressible material, a mesh like this will give you zero displacements everywhere. And therefore, keep on, I'm applying million PSI load, nothing is moving. That's because the mesh is like that now, and have a constraint. Same thing happens if you are doing a plate problem or a beam problem. We say thickness cannot change, right? Because that's in Euler-Bernoulli beam theory. Thickness doesn't change. So that's a constraint. So that can cause problems too. So whenever you have constraint, whether you have a large deformation problem or a small deformation problem, mesh design can give you erroneous results. Erroneous means wrong results. So we have to be careful. That's all one can say. However, if you use a meshless method like MLS or SSPH, you don't encounter this issue because there you don't have, you have particles. These particles are not connected to each other. So you cannot say this particle must move horizontally or vertically. Right? This particle is not connected to anything. So we are safe, or safer, whatever. Excuse me. Generally, we don't encounter that issue. Again, in some situations, you may encounter it, because I cannot rule out every possibility. But generally, we don't encounter that. So the locking issues don't show up in a meshless method. Of course, if you have singularities, then it becomes a big issue. Then it's not easy to simulate. It's not easy to generate basis functions that have the right order of singularity in a meshless method. Whereas in the finite element method, you can enrich your basis functions. In MLS, it works fine, but in SSPH, we made only one attempt with psi. That attempt did not succeed. That does not mean it cannot be done. And I don't have manpower to check other things out. Of course, as I said many times before, I don't write any code myself. But I don't have any manpower to check it if manpower means graduate students. So I don't have any resources to check it out, how to enrich basis functions for SSPH basis functions so that we can simulate similarities. And with MLS, yes, people have done it. With SSPH, I don't know. Okay, any questions on your mind? Yes? Yeah, if you use 800 element, maybe you won't have that problem. No. Well, 600, say. Triangular, 600 triangular, or if I have quadrilateral, I'm 800 quadrilateral. I may not have that issue. I did not say I will not have that issue. 800 is good enough. You look surprised. It's very commonly used, 800 element. No, there's no problem. No, there's no problem. You have notes that Professor Dinesh Kumar emailed to you. It has shape functions for these 800 elements. So there's no problem. Actually, we are right on time. It's 12 o'clock. Any questions? I think it's not probably a great idea to start with the CZM now, because I don't think we can. I will lose your patience because it will take at maybe an hour. So maybe we can do it after the lunch break. Because he asked me, when will I show him 6th-order differential equation? So I have to show you that 6th-order differential equation. So I will do it after lunch. Yes, there are no guarantees that if you use higher order element, there will be no shear locking or there will be no locking. The chances are less. It's not foolproof. Pardon? Yeah. It's another subject. I can't go into it. Because you need to continue mechanics, as Shakti mentioned yesterday. So I need to cover continuum mechanics. And I don't think we can cover everything. I mean, yeah, sorry, we can't cover everything. Pardon me? Yeah, I mean, gelatin is an incompressible material. Your soft tissue is an incompressible material. Rubber is an incompressible material. Water is generally modeled as an incompressible material. Air is modeled as an incompressible material. Yeah, it has to be enforced. You just put ninth node at the center. Eight. No 9 node. I can have 10 nodes too. You need complete polynomials. Complete polynomials. There is no 9 terms don't give you any complete polynomial. 1, yes. No, it's not. It just comes out to the fact that you have complete polynomials. Makes no difference whether you have 4 nodes, 5 nodes, 6 nodes. So long as you have complete polynomials of at least degree 1, the sum will come out to be 1. Take any polynomial, take complete polynomials. Add them up, they must equal 1 everywhere. Finite element basis function, they will equal 1 everywhere. That's why I've been using complete, yes. Yeah. So what is the question?